Thanks for having me. So I'm Sahar, and as Diego said, I'm AI Research Lead at King. Today I was planning to present together with my young fellow, my daughter, but we realized both of us are up for talking a lot. So she's taking a walk and do the talking outside the building, and I do the talking here. In this presentation, I would like to share with you the journey that we have taken to take our research to production in the case of content production automation. So, yes. Okay, so a little bit about King. As most of you might know, King is a gaming company and creates cross-platform casual games. The four global franchises that it's famous for are Candy Crush, Pet Rescue, Farm Heroes, and Bubble Witch. We also continuously innovate on new games, and if we want to talk also about the volume of data and the type of challenges that we have have 250 million monthly active users as of the first quarter of 2022, and we have a large volume of content that is continuously growing. And just to give you an example, in Candy Crush Saga game alone, we have more than 11,000 levels as we speak, and this is continuously growing. It does have a large variety also. So I come from a central team that is working on applied research and also operationalizing machine learning in the company. And we work on three areas. We work on content production automation, user understanding and in-game user experience, and machine learning operation and governance. In particular, today I'm going to talk about content production automation, where our goal is to maintain quality of content at scale and also to maintain and provide a good user experience. So, when I talk about content production automation, we are talking about generating content and validating the content. And of course, we also talk about the infrastructure that is needed in order to be able to provide this content production automation to the game development. So what's game content in the context of Candy Crush Saga? We have, as I mentioned, we have diverse content. So we have various game elements, various blockers, game objectives, and we have different types of move limits. And just to give you a perspective, like for instance, we have regular candies with a special power, long range. We have different types of blockers that they can also stack on top of each other. And we have jellies, locks, and so many other elements. And how does the game work? So, yeah. So here you see an example, a demo of the Candy Crush. It's a match 3 puzzle game. It's a puzzle of size 9 by 9. As you can see, candies of the same color. Yes. Pause here. Yeah, so you can horizontally or vertically match 3 or more candies of the same color, and that leads to clearing the board. Those cells that are part of this match, and then candies will fall randomly from the top to replace them. And as you can see here in this example, we have we have a certain number of frosts that we wanted to clear from the board, and then there's a limited number of moves in which, you need to clear the board, meet the objective in order to be able to successfully finish the game. So with that, what's our goal? Our goal is to create content that provides a good user experience it's fun to play and also fits the journey of the player. So we don't want to continuously have difficult levels or continuously have in our progression of levels continuously easy levels, but a good experience for the player to play. So why content automation? This whole process of content creation starts from creating a new level, which is very fun for designers, and then it's about a large chunk of their time about balancing, modifying it, keep iterating and tweaking to identify if there are broken parts or broken experiences, or if the difficulty is the way that they want it, and make it enjoyable for everyone. And finally, we go through the release process and gradually releasing it. And this is the largest and most time-consuming part. And we thought that we could help them by applying AI to reduce this time. And instead of also having only one-time playtesting of manual playtesting, being able to have multiple of them and very fast. So this helps us to have a faster production pipeline. It could enable us to have better content quality. It also helps us to test and make sure that the player experience is not broken, and test better our levels, and then also in order to have a good knowledge about our levels. So to summarize, our goal is to maintain quality of content at scale and provide a good user experience. So how are we translating it into more detailed objective? We are aiming to build an AI-powered solution that supports human in the loop, and I would like to emphasize on that, by providing automation capabilities including content discovery, health monitoring of live content, evaluation of created levels, and supporting creation of levels. Getting back to this image, I would like to first talk about the validation and the playtesting bot that we use for validation, and then we go through the generation. So what's playtesting bot? So it's probably quite obvious for this community, but it's also important to emphasize that if you compare to state-of-the-art AI bots that are playing games, we are not looking for a bot that is surpassing the best human performance, but rather we are looking for a bot that is playing human-like, and our goal is to assess the quality of the game, not just having the best performing agent. And it's important also for us to keep in mind that we would like to have a bot that has a good generalization and a good coverage on all the variety of objectives that we have and different type of game elements that we have. How do we do that? The very first thing that came into our mind was to apply heuristic. It's simple, it's fast, it's easy to build it, but at the same time, it's also easy to break it. The moment that we are starting introducing new game features, then we can't maintain it anymore. And also, the rule base cannot really simulate human play in our case. And another approach that we started looking at was to apply Monte Carlo research, which is commonly used in AI for games community. And it traverses the search space of possible moves, which does have high accuracy, but in the case of Candy Crush Saga, it would be very slow. So we started looking at an alternative, which is trying deep learning, which could help us to get to better speed, but also having a good accuracy. For those that they are not familiar with supervised learning methods, so the first part that we tried and explored was we applied supervised learning. And what we do is that we give a large number of labeled observations and the machine learning model predicts the label of an unseen observation. So in this case, if we have multiple classes, dog, cat, moose, and whale. So our training model for a new example is trying to predict what's the most probable class. And in this case, we see that this is most likely a cat. So we started saying that if large volume of human player gameplay data is available, can we build an agent that plays more human-like? With that in mind, we started exploring, and what we did was that we take the initial state of we take a state of the board, and then we also look at the corresponding action that the human player took, and then we train, with a large number of data, we are training a model. And for a new state, we are there are different possible type of moves, and our model is predicting which one has the highest probability. We also looked at when evaluating this. Here you see agent success rate, and also you see player success rate, and they are in log scale. And what we can see is that for a majority of tested levels, we see a linear relation between them, and we felt like this is, in terms of our metrics, this is more is human-like play. It also drops here, as you may notice, so it's not particularly doing well in harder levels. How do we present our content? So we take the game state, we look at, we define this as a stack layer of matrices, and we have here several layers. So we encode, for instance, different candy colors each in one layer, and then we have blockers and several other stack layers. So we have more than 100 binary feature layers. And for our action space, so the classes where we are predicting on, we have 144 of them. So each move, left, right, and up, down, is considered as one action to choose from, and we consider them mirrored. So in total, instead of 288, we are using 144 of them. It's a huge action space, and a very sparse also input space. We are using a convolutional, a stack layer of convolutions in order to build our model, and at the end, as I said, we are predicting which action is the most probable one. Here's an example that we have this state, and there are a few possible moves, and we can see their probabilities predicted by the bot, and at the end, the bot takes this move here, which is not necessarily immediately leading to a match tree, but it might lead to a better strategy longer term. We put this playtesting bot into production. Currently, we are using it for different games. And in addition to playing the game, it provides us also a lot of different metrics. For instance, the win rate, the moves available per state, and also how many moves are left when the player is finishing the level. I'm not going to go through this, don't worry. I just wanted to highlight here that there was a huge effort to make this into production and serve it in our production system. We are using cloud platform, and we have a lot of components in order to be able to scale the number of simultaneously scale the number of game environments that we are running and agents that we are running. Okay, so this sounds great, but there are some challenges. So it doesn't, when it comes to new game dynamics or certain types of dynamics that are more complex than just matching tree, for example, conveyor belts that we have, it doesn't generalize that well, and it also requires large volume of data. So if we are talking about end of content in our games, it might become more challenges because we don't have, or very new type of levels, we don't have player data for those. So we started looking at totally exploratory research on reinforcement learning. A bit about reinforcement learning. Let me see how am I doing in terms of time. Okay. A bit about reinforcement learning. So in reinforcement learning, the agent, just if we go one step back in supervised learning, we had an agent that was exposed to a lot of labeled data, learning to extrapolate from that how to predict for an unseen state. Here, the agent is interacting with the environment by taking an action. And each time it observes a state of the game, it takes an action, and based on that, it gets a reward, which tells how well this action was how much this action was contributing to the winning state. So our goal is to maximize the expected accumulated reward, and that's the policy that is the optimal policy is basically trying to maximize the expected accumulated reward. And in our context, so we have the state, and the agent takes one of those actions that I showed previously, and then we see how, like, if it leads in a single agent, if it leads to a win state, that would be +1. If it's leading to lose state, that would be -1. Also, just imagine that, like in parentheses, I have to say that let's imagine that you have 32 moves. That means that you have a sequence of 32 actions to get to a state that is win or lose, and then you need to go back to assign the contributions to each of these states. So we have very sparse reward. When we are talking about deep reinforcement learning, so basically our agent is a deep neural network that is learning a policy. A popular method that was also used in AlphaGo is DQN, or Deep Q network, which basically what it does is that you have a huge neural network that is going to optimize our Q value, maximizing the accumulated expected reward. What it does is that it collects a huge buffer of states and actions and reward and the corresponding state that the agent went to after taking the certain action. And it also creates mini batches of experiences selecting from this buffer, and then goes one iteration through the network to optimize, and it starts from a random policy, let's say, and then with an epsilon greedy, at each iteration decides whether to take the random move or select from the policy that is optimizing. And this continues for over a very, very large number of steps, and we are talking about the magnitude of millions. So there are a large number of extensions of DQN, and so one of the popular one is Rainbow, which is combining, as you can see here, combining a lot of different methods, extensions of DQN together. And we have been exploring and experimenting with the Rainbow method. And we are experimenting our Candy Crush Saga friends. The results that I'm presenting here are based on Candy Crush Saga friends. Okay, so what are the challenges? There are 4 challenges that I would like to highlight here. One is related to application. Then it's about reward selection, generalization, and scalability. So when it comes to application, we need to make sure that the solutions that we are taking from other domains, they are applicable to our domain. And when it comes to reward, I mentioned about the reward that is sparse. So we need a reward that reflects the level objective. And I'll tell you more about those. And it's also about generalization. How do we ensure that it's generalizing well on the various type of levels that we have? And then also scalability. So a lot of papers that are published in deep neural network, in deep reinforcement learning, they are based on results on Atari games, and we are working with the match 3 puzzle game, and we would like to make sure that we consider the applicability when we are building a model. Another thing is about reward. So this is an example that this Coastrunner game, the agent here is optimizing for collecting points, and it starts getting stuck in a local optima because it helps it to keep collecting points rather than continuing and finishing game. So it's important to think of, like, what would be a good reward for a game. So, direction. Okay, generalization. So here I just wanted to highlight an example of, like, if you look at here, the agent that has learned this pattern during the training, when it comes to testing, is not doing well when we go to different sizes of the board and, like, the number of points to collect during the testing. So we would like to make sure that we have a generalizable agent. In our research, we focused on generalization and scalability, and my next point is also on scalability. So this is a GIF showing that, like, how long it took in order to train the AlphaGo 0 to surpass the least adult Go master, and also you see, like, it takes, we're talking about days. But if we are going to production and we want to, like, be able to iterate in our research even for different parameters that we are trying, we would like to talk about days and minutes or hours. And also we would like to be able to use also not just CPUs but also GPU and CPU. So here's an example of, like, a level that we started looking at, talking about generalization and about rewards, and that should reflect also the objective of our game. In this particular level, for instance, we would like to spread jam over the tiles, and the levels, the tiles that are involved in a match 3, if they have a jam on them, they lead to spreading a jam over the rest of the tiles too. So we have a limited number of rooms, and in which we want to spread on 64 tiles jam. So what we experimented with was that we started looking at, for instance, defining rewards that describe spreading the jam, or, like, proportion of the coverage, or, like, how much each step is contributing to the coverage of the jam. And we saw promising results. Then we started thinking about what if we start defining skill-based agents and then combine those agents together. So for instance, instead of, if we go here, instead of learning to only do match 3s and match 4, which is what it matters, think about creating special candies because they have a wider power, wider range of power. For instance, these striped candies can lead to clearing the whole row, or thinking about, like, strategies of removing blockers as an example of a skill. That's what human players do. So we built some agents that they are skill-based, and we saw that, first of all, our agents are learning those skills, but also we saw that they are, if we are combining them, they are performing reasonable. So we started looking at hybrid models of how to combine these agents in order to build a new agent that can play on different levels. And this is, we built a meta agent that is basically learning how to weigh different agents that they are skill-based. And just yesterday we got to know that our industrial PhD student is working on this one, and we got to know that her paper got accepted to ICMLA, and she will present it. So, I mentioned this was a generalization, but we also started looking at scalability. So moving away from just having training only a single instance of game client on a single machine to have a more scalable system. We started experimenting and extending the seed architecture from, if I'm not mistaken, from Google. Yes, from Google AI, and built our own version. And what you see here, for instance, is that the blue line is from the seed rainbow version that we have. And the green one is the rainbow on a single instance. And yeah, it learns faster. Going back to generalization and which directions we would like to take. So we are looking at continuation of looking at skill-based, looking at using player data and being able to build on top of that for skill-based reinforcement learning. And then we have been also experimenting with transfer learning to see if the agent is trained on simpler level, can we bootstrap our learning from that and transfer that learning to build an agent faster in an hour, for instance, or a few minutes to work on a more complex level. Okay, I should go faster. This was playtesting, the large part. Now we are talking about generation. One of the things to consider is that it's very challenging to define what is a good level and to be able to have a good score function. And also, it's very hard for us to measure what is a fun level to play. So we started, instead of just having a machine learning model that generates level, we start considering human expert to be in the loop of our generation. And for the first iteration, we built a tweaking agent that improves the quality of the generated level by designer, or tweaking our live levels to improve them. And recently we also started looking at generation of content. So I'll talk about the tweaking part. So what we do is that we collect problematic levels. A problematic level would be something that, for instance, designers start changing their design principles. So they don't want to have very large number of moves because it becomes very boring for the player to play. So then how do we go back and fix all of those live levels without disturbing the player experience for all of our players? So here, what we do is that we build this agent to identify those problematic levels. We send it to a search engine that selects a number of tweaks. That these tweaks came from the suggestions of our designers. For instance, subtract a layer of blockers, or substitute a layer, or change number of move limits and change number of candy colors and so on. We create a new, we make a small adjustment, and then we send it to our playtesting bot. We collect the score on the tweak level, and then we collect some metrics from the playtesting. We send it to our scoring service, and then we see the quality. One of the things that we should consider is that the level should be playable. That's the criteria that we are considering. And the design guidelines that our designers defining should be also satisfied. So in order to define our metric, we are looking at level definition. So we are trying to preserve the similarity as much as possible. We are trying to respect the symmetry and respect also all the design guidelines that are given to us. And then from playtesting, we get, for instance, the difficulty, so like we want to preserve as much as possible the win rate, and then we also want to reduce poor experience dynamics, for instance, the number of shuffles that the player might get. And shuffle means that there's no possible action to take, and then a board gets to shuffle. So we use the genetic algorithm, we create a population, and then we iterate over and create the best end tweaks and show it to our designers to choose from. Here's an example of as from here to here, these tiles are changed. This is a fan, so it had a locker, the locker is moved, and there might be also some changes that is not obvious on the board, like for instance number of moves. But with minor changes we can keep the difficulty as it was and not also change that much the board. Okay, so what are the summaries and takeaways? So by the way, this is we started testing. It's been like a year and a half project to take it into production. So it's a huge project, and we started testing with this one with our designers. So this is the tiny bit that my team has been working on, and this is the whole thing that is required in order to build our system to work. And that's why I went to the highlight to the infrastructure. And it's a collaborative work with games and with our operation team to be able to build all of this. Just to give you a perspective on timeline, so we started with heuristic methods for our playtesting bot. We went through building the production for supervised learning bot. Then it started research exploration on reinforcement learning, and it started doing content generation. After we have we are confident with the bot that we have. So it's been a really long journey to reach here and be able to build on top of this playtesting bot a lot of different things, such as tweaking. In summary, the road to product, I would like to read it, it's much easier, but the road to product for complex use cases is long and bumpy. And if we realize the need today, we should have started researching the topic a few years back to keep a realistic timeline towards the stakeholders. And I can't emphasize more on this one in industry. Another thing that I would like to say is that integration of the research in game is really also tied to the maturity and adoption from the organizations that we are working with. And again, this has been a huge team effort, and I would like to thank all of my colleagues in machine learning operations, academic collaborations that we have, and all of the engineers from game teams. And thank you.
Thank you, it was fascinating. Questions?
So, in training the initial foundation bot, you train it to play like a player, right? Does it consider sort of the sort of meta aspects of a board state that might change how a player plays? Like looking at it as your last life, right? I could see that changing quite a lot how a player might make their moves. Does it try and consider that sort of thing, or is it just the board state itself?
We only look at the board state and not considering the game economics when we are testing our levels. Yeah.
Hi, thank you, Sahar, for showing us the behind the scenes of actually implementing AI techniques in a big company asking. My question is, as you took a long time to research all of this and to develop the tools needed to have this feature that is important in your game, I'd like to know how adaptable it is. If tomorrow your designers invent a new game mechanic, you basically have to redo the whole thing. Do you think that's the structure that you have allows you to adapt to the new kind of levels you have to create quickly, or is that, do you mean that, or is that a case where you have to do everything from scratch and it will take years again?
Very good question. The reason that it took so long is also to make sure that we don't do that, right? So we did define, first of all, like the research was defined through a lot of internships. And master thesis work. So a lot of explorations happened there, and when we found promising approaches, so we started exploring, keeping in mind that we always are looking at also generalization and scalability, right? Meanwhile, we started also building infrastructure. And so for instance, at the moment, every time that roughly every, let me go one step back. When I joined King, which was like 3 years and a half ago, last time the bot was trained was 2 years before that, right? At the moment, what happens is that every roughly 3 months or 6 months, we retrain the bots for each of the games. At the same time, if designers come to us and say that, hey, we are introducing something new, then we start exploring, testing, retraining the bot. And we just add new game features or look at, for instance, explainability components and so on to see why the bot doesn't perform well on the new levels, and we reiterate on that. But that takes maybe 1-2 days to train it, but also maybe a week to just evaluate and feel comfortable on the results.
Hi. I was interested, have you witnessed any player behavior change based on visual elements like the colors or the animations that play in response to certain actions? And do you include that in your modeling at all?
So, unfortunately, our work has been a bit disconnected from user research work. So I'm not aware of those type of impacts. But at the same time, things like deciding in the initial board what color gets on the board is not something that is defined in the, even when designers are defining the level. It's a random choice. So, and we are not introducing new dynamics that doesn't exist already. So that means that there's been a pre-study and evaluation in the design before we start working. So we are trying to just do minimal changes, not to be intrusive.
Okay, hi. I think you've answered my question partially in these two, but still I'll ask that again. So with this kind of technology, how do you envision the role of game designers evolving, designing games like match 3 kind of games?
So, very good question. In the past 2 years, my role has been working very close with game teams, especially having a focused work group together with designers to have conversations and just making sure that we understand what they need, and also having iteration and feedback from them. I think it we both have evolved and learned from each other and trying to make sure. We started with generating levels at the beginning as a research, and then we realized, oh, this is not really their pain. Tweaking is what's taking a lot of time. So that's where we shifted the application that we are looking at. So I think we are evolving both at the same time, and we are trying to make automation works where they need it and learn from that. Does that answer your question?
It also answers mine to a large extent. So did I was going to ask you what the designers thought. Did they reject some tweaks and levels for interesting reasons, which could play into improved modeling in the future?
Mm-hmm.
And yeah, have any of these gone into games? Is another question.
So yes and yes. So yeah, we have been testing and experimenting with some of these levels, and they have gone through live content. And for feedback from designers, so the whole process is that it doesn't automatically go to the live content. So it goes through a tool for designers. It's still not fully productionized, and so there's still some manual steps to make the full automation happening. But there's an option and an interface for designers to review and provide feedback to us. We are hoping in future, by collecting this feedback, to also have an active learning to improve automatically. But for now, we read their comments. If there are things that are confusing, we go back and talk to them. And a lot of things led to improving the bot for us. Yeah.
I was going to suggest active learning.
Any other question?
Hi. Firstly, just thank you for coming to the keynote today. But secondly, my question would be, you mentioned there about the designers having the feedback and input on the process there. But how much does it go towards user experience and maybe involving some of the end users as well?
So, in general, regardless of if you remember the automation components that I showed, there's the last step that is release. So in general, regardless of how the level is created, when it goes to the release, it's a incremental release. So first is a tech test where it goes through a small percentage of the users. Then it goes to larger, just making sure that nothing breaks. It's the same for all of the all of the applications. So that we do the same, just making sure that we don't feel we see everything offline is working, but through that increment we make sure everything also is reasonable. And then we look at our data scientists start looking at all of the metrics, and designers looking at the design, and then if you feel confident, then we can proceed with that.
Anyone else? Okay. Then I'll use the power of the session chair to ask the last question. So you said in one of your last slides that you wish you had identified the needs earlier to do research on that. So the question is, what are the needs now, and what should we be doing research on?
Very good question. The thing is that, remember I said this is a gradual learning for all of us. It's a bit of also a lot hand-holding, because very often the user does have a hard time to describe what they need in terms of machine learning problem formulation. I would say one of the things that we started exploring recently through an internship is also building explainability component. And if you want to, for instance, generate a new level, how would you consider the feedback that you get actually for meaningful, first of all, explain how things are learned and what are the things that are learned, and also how we can incorporate the input of designers in an automatic way, or have a latent space, for instance, based on those that we can update and generate models. So I would say that is one. Then the playtesting, definitely, I think the generalization and scalability still is a huge field to look into.
Okay, that's all fantastic. We have 2 new students starting doing explainability and playtesting. So just in case these are placement opportunities.
Cool. We can catch up and talk about that.
So let's catch up on that, definitely. Let's catch up.
I'm definitely interested.
Okay, great. Right, let me thank you again.